Hi everyone, my name is Yi. I'm engineer from TenCap. Today I'm going to give the presentation serving Chilean record table on TiKV. So in this presentation, I will talk about what TiKV is and shows the overview of architecture of TiKV. And I'll then introduce the Zhihu's use case, which is the largest TiKV cluster that we are aware of. We'll talk about Zhihu's use case for storing the reading history data in TiKV and also their next generation for the infrastructure for the same use case, which is the Zeta table store. And after that, I'll talk about two features that have been useful for the Zhihu's use case, which is the transaction and follower read. And that's it. So first, what is TiKV? TiKV is a distributed transactional key value database that was originally created at TenCap as the underlying storage layer for TiDB. And although usually used together with TiDB, TiKV can be used as a standalone key value database. And the design of TiKV is inspired by Google Spanner and HBase, but it is simpler to manage and it does not depend on any distributed file system. The project is right now a CNCF incubating project, and we are trying to move this TiKV to graduation stage this year. TiKV has over 7,000 GitHub stars, and it's right now have around 250 contributors. So TiKV provides a simple key value API, but it's also able to provide a horizontal scalability, which means that whenever you want to scale up the TiKV cluster, you can simply add machines to the cluster, and the cluster will auto scale up without you worry about doing a resharding to your data. And also, TiKV offers a high availability thanks to the underlying RAP replication. And also, TiKV natively supports transaction. This is a picture showing the overall architecture of TiKV. In the front end, TiKV provides a simple transactional KV API. It also exposes a coprocessor API, which handles push-down aggregation requests from TiDB. It has a transaction layer which handles distributed transaction and multi-version concurrency control. It uses RAF to replicate data, and it uses RocksDB as the underlying storage engine. And we are also working on making the storage engine pluggable, so in the future, we may be able to use other types of storage engines. And this picture shows how data is organized inside a TiKV cluster. The full key range is split into small areas, and each of this area, we call it a region. And the region is the unit for replication in TiKV. And by default, each region will have 3 replicas, and those replicas will be scattered around in different TiKV nodes. And when the workload changes, some of the regions can get more traffic than the other region, and some regions can grow oversized. And TiKV rely on another component to do load balance, which is the placement driver or PD. The PD cluster will basically stores the metadata for all the regions, and it also monitors the workload and the data size of each of the region. And if needed, it will instruct TiKV nodes to move the regions around, move the leaders of the regions around, and also split or merge some of the regions. This is a rough timeline for TiKV development. It was first created on 2015 as a storage layer for TiDB, and 1 year later, we open source it. On 2018, TiKV entered CNCF as a sandbox project and then become an incubating project. And this year, we released the 4th major release of TiKV. Now let's take a look at Zhihu's use case, which is currently the largest TiKV deployment we know of. So Zhihu is the Chinese question and answer website. You can think of it as Quora. And the website is really popular in China, and Zhihu is using TiKV to store the reading history of the users on the website. And this is the dashboard, a snapshot of the dashboard of the TiKV cluster. In this use case, as you can see, the data size is really huge. It's currently having 500 terabyte data, and the data size is still growing. And the cluster has over 200 TiKV nodes. About the use case, the reading history of the users is used to filter the recommendations. So a user won't see an article that he already reappear in the recommendation list. And also the data is used to train models to personalize the recommendation to the users. The data set is currently having a 2.5 trillion records so far, and the data set is still growing due to the fast growing user base of Zhihu and the growing user activities. While having a large data set, the cluster also needs to handle a large volume of read and write operations. And during peak time, the cluster can have around 200,000 records per second writes. And the cluster also normally have 150,000 queries per second for reads. And under this read and write pressure, the cluster is able to achieve a P99.9 latency of around 100 milliseconds. This is an overall architecture for the use case. At the very front end, the Zhihu has a proxy layer. And then there is a Redis cache layer that handles the large volume of read traffic. The cache is a write-through cache. The writes will hit the underlying database, which is TiDB. And TiDB uses TiKV as the underlying storage layer. And the cache layer also subscribe to TiDB changes via TiDB binlog to achieve eventual consistency. Before using TiDB and TiKV, Zhihu used to use MySQL and to store the reading history data. And as the data grows larger and larger, they need to reshard the data from time to time, which is a heavy operation for them. And after they switch to use TiDB and TiKV, when the data grows, what they do is simply add more hosts to the cluster, and the cluster can automatically scale up. And so it's easier for them to handle the increasing workload and the data size. And also, when a TiKV server is down, they see nearly no impact to the overall healthiness of the use case due to the high availability provided by TiKV. And also, as the data size grows, Zhihu also moved to use the cross-cloud provider deployment. And during this transition, TiKV is being very stable for them. So they are currently very happy with TiKV in the reading history use case. But as they add more use case to their system, they want to expand the feature set. So they are building a next generation infrastructure for the same use case. This new infrastructure is called Zeta Table Store. The Zeta Table Store is still based on TiKV, and from the TiKV dashboard of this cluster, and you can see the data size is right now at around 70 petabyte, and it consists of around 100 TiKV nodes. And the Zeta Table Store is right now basically storing the same set of data as the reading history cluster, but the data size is several times smaller due to some clever optimization on the application side to reduce redundant data. Zeta Table Store features a NoSQL API, and it provides transaction and secondary index support. It provides a native Y-column data model, and the data in it can have schema or be schema-free. And most importantly, the Zeta Table Store is still based on TiKV, so Zhihu can still enjoy the availability and scalability provided by TiKV. And also, they make use of some of the TiKV features. For example, the transaction and secondary index support are all based on TiKV transactions. This is overall architecture of the Zeta table store. We won't go into detail here, but as you can see, TiKV is still being used as the storage layer, and most of the other nodes are stateless. And this is a demonstration of the Y-column data model provided by Zeta table store. And as Zhihu switched their traffic from the existing reading history cluster to the newer Zeta table store, they also plan to add more features to their system, including multiple protocol support, optional relaxed consistency level, and also they plan to build big data connector and full test search capacity. And for the last two items, they plan to have those systems integrate with the TiKV cluster on the replication level, and we'll talk about that in a bit. So let's talk about transaction in TiKV, which transaction is proved to be very useful for the Zhihu's use case. Is simplify their application logic. They don't need to re-implement transaction in their application layer. So to have transaction, because data in TiKV are split into small regions, and those rough leaders for each of the regions can be on different TiKV nodes. So to run a transaction, we need to do a distributed transaction over multiple rough groups. And this is done in TiKV using the percolator model. The percolator model is described in the Google Percolator paper, and we use it to support both optimistic transaction and pessimistic transaction. This is an example of the percolator model. It is basically a two-phase commit protocol, and in this model, all the data are split into three columns: the data column, the log column, and the write column. And in TiKV, we use RocksDB's column family to implement those columns. And in this example, we have a transaction writing to two keys, A and B. And for each transaction, we need to choose a primary key. So here we choose key A as the primary key. And during the pre-write phase, we will write the new data to the data column with a timestamp. And also we will place a log to each of the key in this transaction. And the logs will have a pointer pointing to the primary key. And in the commit phase, only the key A, which is the primary key, will be updated. So the write column of key A will be updated to denote that the transaction has been committed, and also the logs on key A is deleted. Since only the primary key is being updated in the commit phase, it can be done in an atomic way to a single rough group. And the logs and the write columns for the other keys will get updated as we resolve the logs in subsequent read or background GC thread. When we resolve a log, we will make use of the pointer to the primary key to confirm that this transaction is committed. So this is how we initially implement optimistic transaction in TiKV. And in the latest version, we also want to implement a pessimistic transaction. And how do we do that? It turns out that it only require a very simple change. So for pessimistic transaction, and we have an actual locking phrase. And during the locking phrase, we'll place a log to all the keys in this transaction. And the log will have a special flag, which signify that this log is a pessimistic log. And in the pre-write phrase, the pessimistic log is turned into an optimistic log. The log format is the same as in optimistic transaction, so that and the rest, the flow for pre-write and commit phrase are the same as optimistic transaction. In this way, pessimistic transaction and optimistic transaction in TiKV are compatible with each other. So you can have two clients connected to the same TiKV cluster, and one client doing a pessimistic transaction and one client doing optimistic transaction, and it's perfectly fine. For pessimistic transaction, we also implement a deadlock detection. So for deadlock detection, we will in a TiKV cluster, we will have one TiKV node to play the role of the deadlock detector. And to simplify the implementation, we use region 1's leader as the deadlock detector. And also on each of the TiKV nodes, there is a waiter manager. And a transaction wants to lock a key. If a transaction wants to lock a key and then finds the key has been locked by another transaction, it has to wait at the waiter manager. And the waiter manager will use the information to update the dependency graph on the deadlock detector node. And if a deadlock is detected, the deadlock detector will notify the waiter manager to abort one of the transactions. So the overall design is very simple, and there is one tricky case. So when there is a leader transfer happen, and the region 1's leader transfer to a new TiKV node, this new deadlock detector will lose all the previous information on the dependency graph. And what we do to resolve this issue is very simple. We are not trying to keep the dependency graph up to date. In this case, we simply rely on the transaction timeout to retry themselves. So that's it for transaction. And another thing I want to talk about is follow-a-re that we recently add to TiKV. Follow-a-re is an optimization in the ROC protocol to reduce re latency. And to understand what it is, we need some basic background knowledge for the ROC protocol. ROC is a consensus algorithm, and a consensus algorithm basically have two goals. The first one is to ensure an agreement on shared state among all the nodes in a cluster. For TiKV, the shared state is the state of the data stored in TiKV. Another goal of a consensus algorithm is to recover the cluster from server failures autonomously. So the ROC algorithm achieves these two goals by doing a log replication. And I'm going to use TiKV as an example to explain how log replication works. So when the client wants to write a piece of data, it will send a request to the corresponding ROC group leader. The leader will translate the request into a log entry and then start the log replication. The log replication consists of two steps. The first step is the commit log. In this step, the leader will append the log entry to its local log, and at the same time, it will broadcast a message to replicate the log entry to all its followers. And once it makes sure that the log entry has been replicated to a majority of the replicas, it proceeds to the next step, which is apply log. The content of the log entry will be applied to the local state machine on the leader. For TiKV, the state machine is just the underlying KV store or ROC city. And after that, the leader will return to the client. And all the followers, once receive the log entry, they will apply the log to their local state machine asynchronously. So this is how a write in TiKV works and how does re works. So for re, it is usually done in the form of a re-index. So when a client wants to read a piece of data, it sends a request to one of the nodes in the ROC group. And in case it hits a follower in the ROC group, the follower will need to send a re-index request to the leader. The leader will then look at its committed index, which is the index of the latest log entry that has been committed. Then it will broadcast a message to confirm the liveness of this committed index, and then after that, it will read the data at the committed index or on its own state machine, and then return the data to the follower. And as you can see here, the re-index has still drawback, and so the second step can be optimized out by using an optimization called list re. But still, Another drawback is that the reindex needs to in reindex the data are always read from the state machine on the leader, and which incur more I/O on the leader, and also it incur network latency between the leader and follower, and the network latency will be more noticeable when the follower and the leader are on different data centers. So there is a followery to solve the problem. In a followery, when the follower receives the read request, it will send a modified version of reindex to the leader. And the leader still needs to confirm the liveness of the committed index. But this time, instead of reading data from its local state machine, it returns the committed index directly. And the follower will use the committed index to read from its local state machine to get the data and return to the client. So, so the followery is generally useful in case the follower and the leader is on different data center, and also it's more useful when the data being read is large in size. In the Zhihu's use case, they make use of followery to help reduce latency, and also they plan to use followery in a more creative way. So this is the demonstration of their planned use case. They plan to add a data warehouse in their system, but this data warehouse is in a different data center. And what they plan to do, instead of building a ETL pipeline to stream the data from a TiKV cluster to the data warehouse, what they plan to do is to have the data warehouse participate in the rough replication of the TiKV cluster. And then for reads on the data warehouse, they will use follow read. There are some benefits for this setup. One of them is, of course, the OLAP workloads will now hit the data warehouse where the query can be better handled. And also by using follow read, the cross data center traffic can be reduced. And also, since the data warehouse participate in the rough replication, it can play the role of one replica in the system. And so for Zhihu, they can reduce one replica in the TiKV cluster in their main data center to reduce cost. And this usage is very creative, and we are looking forward to see how it goes in the future development. And that's it. That's it for my presentation. And if you want to know more about TiKV, here are a few more links, and we will always be available on TiKV Slack channel for any questions. Thank you. Hi. Hi, thanks everyone for joining. Any question? Oh, so we got a question. What are the re characteristics and how many re operations are possible, and how to optimize for that? Actually, today I have Xiaoguang Sun, who's the lead of the Zhihu's infrastructure team, with me over the internet, and so I'll turn to him for the answer. Hi, Xiaoguang. I don't think they can hear you, but I can relay your question. Yeah. So so at peak the reads are at um ho- uh six one 160 million records per second. Yeah. Yeah. That's the number of records per second. And I think for the Hi Xiaoguang, for the reads, I think they are point get mostly, or are they do yeah they're point get mostly, so we are not using type flash to optimize them. So the next question is when running in multiple data centers, how are transactions dealt with? So right now, I think this question is mostly for TiKV and TiDB, and so I think so right now we don't have a special handling for vendor data in multiple data centers, so we still use the same percolator model for running the transaction. So yeah, so they still need to go over the data centers. We still incur cross data center traffic for transaction. Oh, if you are if this question is referring to the last the use case described at the end of the video, so the quorum will reach inside the main data center. So in that case we can keep the latency low. So the next question, how did you get into building databases? It's complicated. It looks awesome, but way over my head. So I am yeah. There is a lot interesting story about how PinCap builds this database. So, but I think. um, so basically so the founder of ThinkCap wants to build something that's open source and that can make people people can use it. So yeah, I'm not sure about how to answer this question. Yeah, I think all the questions are answered. Yeah, for any questions, you can if you have any further questions, you can go to the Slack channel for question. Thank you all for joining.